Hello everyone, welcome to my YouTube channel School of Chemistry. So today we are going to study about hybridization. So what is hybridization? The process of intermixing of atomic orbitals belonging to the same atom having slightly different energies so that new atomic orbitals of equal energy and shape can be formed is known as hybridization. Now let us study the types of hybridization. What are the various types of hybridization? So the first hybridization which we have to study is SP hybridization. As the name suggests, in the SP hybridization, one S and one P orbital is involved in the hybridization. So it will have 50%, or you can say the hybrid orbital will have 50% of S character and 50% of P character. So this type of hybridization can be seen in BeCl2. So when we write down the electronic configuration for beryllium, it should be 1s2, 2s2, atomic number 4. So it has 2 electron in the outermost shell, that is having 2 electron in the 2s orbital. So this is the case when the 2 electrons are present in the 2s orbital in the ground state. We can draw the p orbital like this, the 2p orbital which is vacant. So in the what happens in the excited state, when this atom is approached by the chlorine atom, one of the electron from the 2s jumps to the 2p orbital, and in the excited state we can write down one of the electron will be present in the 2s orbital and one moves to the 2p orbital. So this one is 2p orbital, 2s. So we have one unpaired electron in the 2s orbital and one unpaired electron in the 2p orbital. These two orbitals undergo the process of hybridization and give us two new hybrid orbitals of equal shape and energy, and they could be represented by this. This is the positive lobe. Bigger lobe is represented with the positive sign and smaller lobe is represented with a negative sign. So these two hybrid orbitals, how many? Two hybrid orbitals will be formed because the two orbitals are involved in the process of hybridization. They align themselves in 3 dimensions in such a way that they will have minimum repulsion and maximum stability. So in order to have minimum repulsion and maximum stability, they would align themselves in an angle of 180 degree to each other. So they would be present like this. Okay. So the chlorine atom with its empty p orbital overlaps this hybrid orbital and leads to the formation of a sigma bond. The other chlorine on the other side, that will be also having its p orbital, that's also overlap with this hybrid orbital, and that also lead to the formation of a sigma bond. So this is how BeCl2 or beryllium dichloride is formed involving sp hybridization. It is also known as a linear hybridization as the orbitals are lying at an angle of 180 degree to each other. Next hybridization is SP2. As the name suggests, in this, one s orbital and two p orbitals are involved in hybridization. So we'll be getting three new hybrid orbitals are obtained of equal energy and shape. Equal energy and shape. Now these three orbitals are going to align themselves in three dimensions in such a way that they will have minimum repulsion and maximum stability. So in order to have minimum repulsion and maximum stability, suppose if we have three hybrid orbitals, then they will align themselves at an angle of 120 degree to each other, means trigonal planar like this. Okay, so these are the three hybrid orbitals which will be align themselves in three dimension. So let us take an example of BH3 boron trihydride or boron hydride we can say. Okay, so when we write down the electronic configuration for boron, we can write it as 1s2 2s2 2p1. It will be having two electrons in the 2s orbital and one electron in the 2p orbital. 2p we are going to represent 1, 2s we are having 2 electrons. So this is the electronic configuration in the ground state. Now what happens when these hydrogen atom are going to approach this boron, then one of the electron from the 2s orbital jumps to the 2p orbital due to the repulsion caused by the electrons of the hydrogen. So in excited state we can write down the electronic configuration as we will have one electron in the 2s orbital and two electrons in the 2p orbital. Now every hydrogen tends to bind with the 2s. Nobody is going to bind with the 2p. Why so? Because it's of higher energy. Every hydrogen needs to be stable, so they all tends to bind with the 2s orbital. So in order to solve the problem, they undergo the process of hybridization, which is sp2, means 1s and 2p orbital will be involved in the hybridization, and we'll be getting three new hybrid orbitals of equal energy and shape. So let us take the example of boron. So in boron we are getting these three new hybrid orbitals. So they are going to align themselves in three dimension at an angle of 120 degree with each other, and the hydrogen atom are going to overlap with them, forming sigma bonds. So this is a sigma bond. Another hydrogen atom going to be present over here, forming one more sigma bond, and the third hydrogen atom would overlap with the third hybrid orbital, forming the next sigma bond. Okay, so as we can see, the shape of the molecule is trigonal planar, so it is also known as trigonal hybridization. Okay, and the angle between the hybrid orbitals would be of 120 degrees. So this angle could be represented as 120 degree. All the angles are equal, that is a 120 degree. Next type of hybridization, that is third type, is SP3. As the name suggests, one s orbital and three p orbitals are involved in hybridization, leading to the formation of four new hybrid orbitals of equal energy and shape will be formed. In order to study this sp3 hybridization, let us take an example of CH4. So as we all know about carbon, electronic configuration of carbon could be written as 1s2, 2s2, 2p2. In the outermost orbitals, it has 2 electrons in the 2s orbital and 2 electron in the 2p orbital. So it has only 2 unpaired electrons, so it should form only 2 bond. So how is going to bind with the 4 hydrogen atom? So this is the electronic configuration in the ground state. In the excited state, what happens? One of the electron from the 2s jumps to the 2p orbital. Again, this is due to the repulsion caused by the hydrogen atoms. So in the excited state, we can write it as one electron is left in the 2s orbital and 3 electrons are present in the 2p orbital, 2p, and they undergo the process known as hybridization, which is SP3 hybridization, forming 4 new hybrid orbitals of equal shape and energy. So now these 4 hybrid orbitals are going to align themselves in 3 dimension in such a way that they will have minimum repulsion and maximum stability. In order to have this minimum repulsion and maximum stability, it will acquire a tetrahedral arrangement. Okay, with a bond angle of, or you can say angle between the orbitals, that will be 109 degree 28 minutes, and the hydrogen atoms are going to overlap with them, leading to the formation of sigma bond. So sigma, sigma over here, one more hydrogen atom forming the sigma bond, and this is the hydrogen forming one more sigma bond. Okay, so this is how the molecule of CH4 is formed, involving sp3 hybridization. We can involve the d orbital also in the hybridization, that would lead to the formation of sp3d, sp3d2 and sp3d3 hybridization. Hope you are clear about this topic hybridization till now. And in my coming video we will talk about the sp3d, sp3d2 and sp3d3 type of hybridization in various organic molecules. One more tip for the students who are watching this video is that in any of the carbon compound you can directly predict out the type of hybridization that carbon is undergoing, that is by counting the number of sigma bond formed by that carbon atom. For example, let me tell you, we have a molecule CH3, CH double bond, CH and CH3. If we talk about this first carbon, how many sigma bonds are formed by it? So 3 with the hydrogen atom, 1 with the other carbon. So it forms 4 sigma bond. This one forms 3 sigma and 1 pi. This carbon 3 sigma 1 pi. As a multiple bond is a pi bond, you can say first bond is sigma bond, second is a pi bond, and in this it will only have the sigma bond. So when we'll be having this 4 sigma bonds, then you can directly write down the hybridization of this carbon to be as sp3, 3 sigma and 1 pi. We can write down the hybridization as sp2. Again 3 sigma 1 pi, hybridization would be sp2. 4 sigma, hybridization would be sp3. If would be having only 2 sigma bond, then hybridization would be sp. Hope my videos are helping you in your studies. So for more interesting video, please like and subscribe to my YouTube channel, School of Chemistry. Thank you.